Welcome to tonight's webinar presented by Professional Educators of Tennessee. I am Samantha Bates, and our presenter tonight is Nancy Caukin. She has worked in outdoor education for 7 years before her 15-year tenure as a high school science teacher at Eagleville School, a rural pre-K through 12th grade school of less than 1,000 students. She currently is a teacher educator at Middle Tennessee State University's Womack Family Department of Educational Leadership, where she began as a tenure-track faculty member in the fall of 2014. Her research interest has been studying the effects of using a science writing heuristic on science achievement, science self-efficacy, and scientific epistemological view of students of different genders, socioeconomic status, and grade point averages. She is also currently researching the effect of a new problem-based learning teacher preparatory course on pre-service teacher sense of self-efficacy. Her future interests are in comparing scientific epistemological views of pre-service science teachers with pre-service teachers of different majors. And if you have any questions at any point tonight during the presentation, you can use the chat feature or the questions tab. If you raise your hand, that doesn't do anything. I'll just put your hand down. So if you do have a question, please don't hesitate to ask, but use the chat or questions tab, and I'll ask that to Ms. Caukin. This webinar is being recorded, and you will receive a professional development certificate shortly upon its completion. I'm going to turn it over to Ms. Caukin.
Okay.
Take it away.
All right. Thank you, Samantha. I appreciate your introduction, and sorry about that long epistemological view. That is certainly a tongue twister there. My name is Nancy Caukin, and I'm at Middle Tennessee State University, and the webinar that I'm going to be presenting today is titled Exploring a Science Writing Heuristic, Supporting the Next Generation Science Standards and Common Core State Standards. The first thing I'm going to talk to you about is what is a science writing heuristic. So a science writing heuristic is a student-centered, guided inquiry teaching strategy where students design labs based on their questions, but they're also guided by the standards. And through this process, students make claims based on evidence that they collect. They share their results with their peers, and they compare their results to the scientific community. And they also reflect on their experiences. The science writing heuristic has been used in elementary, middle, and high school, as well as post-secondary schools, all successfully. It was created by Keyes, Hand, Prain, and Collins in 1999. They have two templates, a student template and a teacher template. Oh my goodness. Are you there? Can you see my screen now?
Yes, I am here, and I see your screen.
Okay. Okay, because now it was showing me that it was off air. Okay, here we go. I modified the template in 2011. And here we go. The original can be found in the Journal of Research in Science Teaching, and I'll move on from there. This is what my template looks like, and I'm going to be going through each of these pieces. So let's take a closer look. First thing we need to do is identify the content standard that we want to address in the lab. We also want to identify the type of laboratory experience we want our students to have, and we want to identify the objectives of the experience. As always, we need to activate our students' prior knowledge. This can be done many ways. It can be done through concept mapping, through a think, pair, share, through discussion, classroom discussion, or it can be done through a pre-assessment. Once we activate our students' prior knowledge, we need to engage their curiosity. We can do this through a demonstration, describe an event, through a video, or even a problem-based scenario. So when we look at the template, the first thing says objectives. What is my question? So we need to guide the students to ask the right questions, and we do this through this discrepant event or this demonstration. And when we say the right questions, what I mean by that is that the question needs to be able to answer the standard. It needs to be based on that standard. It needs to be a testable question, and it needs to be feasible. And when I say feasible, I mean it needs to be able to be done in the amount of time that you've allotted. It needs to be able to use the resources that you have access to. And this becomes the student's objective. It's their question. So next, our partners. We've got to determine how we're going to group our students. Well, one way to do this is once the demonstration or discrepant event happens, you engage students to help them come up with some questions as it relates to what they saw, and you can group your students on similar questions. Or, as a teacher, you know what students work well together and which ones don't, and so it may be that you want to group them how you deem best, and then have the activating strategy and then have them in groups come up with those questions. Next is the procedure. The students have to decide, what are we going to do? How are we going to answer this question? So the students design the experience. Now, it can be framed by the teacher. Now, how much scaffolding you give depends on the content and the context that you're working with in your group of students. Next are safety and materials. So when it comes to safety, so the students, they've seen this thing happen, they're asking questions, they are grouped, and then they design a way to answer their question. Then they need to go back and look at what are the safety issues involved in this experiment. So the students identify the safety measures, but the teacher needs to verify that they have thought of all the safety measures. With the materials, again, the students go back and they identify what they need in order to conduct the experiment. Or it could be that the teacher says, okay, you have to design an experiment using only these materials. So those are two different ways. Once the students have designed the experience, they have their safety in place, and they have their materials list, then they go to the teacher, and the teacher looks it over, and they either give the okay to proceed, or the teacher asks questions to prompt students to change their ideas. So for example, if they have left off, let's say they're using glassware, and they have left off what to do in the event of broken glassware, that they need to be looking for chipped or cracked or starred glass. The teacher would then ask questions to prompt their thinking in order to get them to see what they're missing. Now, as it relates to the procedure, as the teacher, if I see that, oh my gosh, what they have planned, this will never work, as long as there are no safety issues, I let them proceed, because we learn from failure as well as success. Now, again, if there are any safety issues, then absolutely not. Those have to be addressed. But otherwise, I let them try it out. Next is the hypothesis. So first of all, let me preface this by saying that not all experiences require a hypothesis. It may be that we're just making observations. We're looking at what is. But if there is a hypothesis, I have my students typically frame it in an if, then, and then because. And the because part you don't typically see, but it's a window into my students thinking, why do you think this? Why do you have this hypothesis? Next, the students record their observations. So in the observations, the students record what did I see, what did I hear, what did I smell. This is where they gather their data and organize it, and this is where they have their explanations and their equations and their calculations. This is very dense. Next are claims and evidence and claims shared. So when we look at claims and evidence, students, based on the experiences that they have, they make claims about what they saw and then provide the evidence. So they have these statements, I can claim because. Now the claims shared section, this is where each individual lab group will then share with the other lab groups. And there are two different ways that I typically do this, depending upon the nature of the experience. Sometimes I'll have a class data table on the whiteboard in the front of the room, and a representative from each group will come up and they will put their data into the proper place. And as an entire class, we will then look at that data. We analyze that data. We have discussions about it. We talk about outliers. What do these trends mean? What's happening? And the students, I use a scientist's notebook, and they have to record that class data table and give their description and their analysis after we have a class discussion. Another way I do this is with group whiteboards. So I had like 2 foot by 3 foot whiteboards that every lab group would get, and the students would put their results on this whiteboard, and I would have them express what they found in multiple ways. They had to do it textually, so they had to write down what the results were. They have to also do it graphically, so they have to show a graph showing their data. And then they also had to do it, what I would say, pictorially, drawing images of what happened. And they would share that. We would get in what's called a board meeting, circle up with our whiteboards, and each group would then talk about what they experienced, what they can claim based on their evidence, and it gives students an opportunity to ask questions, other students to defend their findings, and engage in discourse. After claims shared comes compared to scientists. So I've designed a lab as a student, and I've identified safety measures and materials, and I get permission to proceed, and I engage in this lab with my lab partners. We're collecting all this data, and we've made claims and evidence, and we've shared that with the class. Now, with compare to scientists, we're going to look at what the scientific community says about our results. And so I used this with chemistry, high school chemistry students, and I would have them research what the scientific community says about what they found. So this could be, they could use their textbook, they could use internet sources, and I always spend a little time in the beginning showing them how to determine what was a reliable source. And then they would need to summarize what they found in their source and compare it to what they found. And they would have to cite their source. And with chemistry students, high school chemistry students, they needed a minimum of 3 comparisons. And of course, that can be modified depending upon the group of students you have. Next is the reflection. So if you have a hypothesis, it's based on that hypothesis. How does this compare to what you thought would happen? Have your ideas changed? Why have they changed? And then the writing portion. And this is an area that I put a lot of emphasis on. It's sort of this conclusion. And with the writing portion, this is done, I have them do it narrative. It takes lots of space, you know, how long sort of depends on your context, but I want the best explanation of what they learned. What did you learn about the objective, the point of this experience? What did you learn about the process, this engaging in science as scientists do? What did you learn about yourself? And what did you learn about the group? Finally is the opinion, and you don't see this very often, but this is important in my opinion, because I want to know what the students thought about the lab. Did they find it challenging? Did they find it interesting? Was it engaging? Was it boring? Was it dull? Was it tedious? And then also, I want to know if you could change something, knowing what you know now, what would you do differently? And first of all, I find that students are grateful to have their opinion asked, and I read them and I refer to them so they know that I've read them. And they like to give their opinion, but it also causes them to reflect again on the process and what they might do differently. So I want to pause just for a minute. That's the first part. I've got 4 parts just to answer any questions that might be out there. And I'll move on. So the second thing I'm going to talk about is how using a science writing heuristic supports the Common Core state standards, or in Tennessee, the TN Core. So the Common Core state standards for English language arts says that students should be able to read and write across the curriculum. Well, if we look at science writing heuristics, students do this, and they do it in the comparative scientists. So remember, they're doing research, they're writing summaries and comparisons and citing evidence, or are making citations. They also do this in the reflection and the writing, and so they're referring to what happened within the experiment and also using what they learned from the scientific community. The standards also say that students need to be able to make claims based on sound, relevant evidence. Well, this obviously happens during the claims and evidence portion as well as the claims shared. So remember, claims and evidence, after they engage in their laboratory experience, they make claims based on their evidence. And in the claims shared, this is where they do this within the whole class group. The standards say that students should be able to form and write opinions and arguments based on their claims and evidence. Again, we see this during the claims and evidence portion, as well as the claims shared. So they're creating arguments, defending what their findings were. The standards say that students should be able to conduct short research briefs, as is common in the workplace. Students do this during their comparative scientists. Again, they're going out, they're researching what the scientific community says about what they engaged in and their results. The standards also say that students should be able to understand, interpret, and evaluate information, whether it's through listening through individuals and through the media, as well as express their ideas, their research, and their understandings in both small groups and larger groups, and both formal and informal settings. And with the science writing heuristic, students do this in the claims shared portion. And there's some examples of the whiteboards there. One thing that I have found in engaging students in this teaching strategy, as they progress throughout the course of a year, their academic language increases. As they engage in this process, they're reading, they're writing, and they're talking, and their academic language, as it relates to the content, does increase, which is what the standards call for. Now, there are 8 mathematical practices, and so I'm just going to go through those very quickly. Make sense of problems and persevere in solving them. Reason abstractly and quantitatively. Construct viable arguments and critique the reasoning of others. Model with mathematics. Use appropriate tools strategically. Attend to precision. Look for and make use of structure, and look for and express regularity and repeated reasoning. So of these 8 standards, of course, any of them could be woven into a science writing heuristic experience, depending upon the content that you choose to use. However, I would argue that there are 4 of the mathematical practices that are inherent in what we do as we engage students in science writing heuristic. And that's number 1, number 3, number 5, and number 6. So we are supporting Common Core and 10 Core standards, both English language arts and mathematics. Any questions? Okay, we're going to move on to how using the science writing heuristic supports the next generation science standards. So we're going to be looking at what we call practices in science and engineering. And as I go through these, it's very apparent, the support. So the next generation science standards say that students need to ask the questions and define the problems. And that's what's happening. They develop and use models. So in their whiteboards, when they do their board meeting and they're constructing graphical representations, that's a way of modeling. And sometimes they come up with physical models as well. Students plan and carry out investigations. They analyze and interpret data. They use mathematics and computational thinking. They construct explanations and design solutions. They engage in argument from evidence. They obtain, evaluate, and communicate information. And you can see very obviously that all of those practices happen regularly using science writing heuristic.
No questions.
Okay. So now I'm going to tell you about how using a science writing heuristic increased my students' science self-efficacy, and this is how it impacted their attitude towards science. So I've conducted 4 cycles of research using a science writing heuristic. I measured quantitatively the change in students' science achievement, their epistemological view, and their science self-efficacy. I disaggregated this by gender, socioeconomic status, and grade point average. And I measured qualitatively students' perceptions of how using the science writing heuristic helped them to learn and problem solve. So I'm going to be focusing on just the qualitative portion, the self-efficacy. So after participating in a science writing heuristic, students reported the following, and this is what I gathered through surveys. Students said they learned how and enjoyed designing their own labs. They thought it was a better way to learn science. They learned to problem solve. They said their self-confidence increased. They learned how to explain scientific principles in their own words. And that reflecting on their experiences helped them to learn and think for themselves. So I want to just share some quotes with you from my high school chemistry students. One student said that it makes me feel a lot more scientific because it made me come up with my own way of doing things. Another student said, these labs helped me become more independent so that I could be more of my own scientist. Another student said, I'm not very good at science, but in labs I'm confident because I know what I'm doing. And maybe as a student you've had the experience of engaging in a science lab and you followed the directions and you did what you were supposed to do and you had some results, but you really don't know why you were doing that or really what it meant. And so this is powerful when a student says that I know what I'm doing and I'm confident because I designed it. Another student said, the writing portion in labs helped me to really learn, not just memorize. By writing, I was able to absorb the knowledge and then explain it in my own words. And when you can explain something in your own words, then that means that you have integrated that knowledge, you've attached it to your schema, so that too is very powerful. And the thing that's important to me is that it's through the writing, that going through this process, that process of writing is very important in learning. Another student said it helped me to actually know what we were doing by me designing it and writing it down because it made me think about it more. Another student said, I learned responsibility and to be a better thinker. So problem solving. I did a training with some 5th and 6th grade teachers who implemented science writing heuristic for at least one lesson, and I just have a couple quotes I wanted to share with them from them. One teacher said students were easily able to follow directions, stay on task, and learn. Another teacher said, my kids can be chatty during projects, and I had some reservation about that. They pleasantly surprised me by remaining on task with this project. I love the implementation of writing. This was a great lesson to begin to understand the scientific method. I based all other lessons with this scientific method format. I really enjoyed the reflections the students wrote at the end of the learning. It was a great form of evaluation, and I will second that. It really makes the students' learning visible. So you may want to know, how do I implement science writing heuristic in my classroom? Well, I would suggest that you start small and don't get overwhelmed. Maybe you just pick a lab that you already do. So you look at your standards, you have this lab that you already do, and you can begin to think about how could I adapt this thing that I do to sort of fit this template, to give them this experience where the students are really engaging in science as scientists do, because that's really ultimately we want to happen. We want them to be scientists, to think of themselves as scientists, and to engage in learning through this process. So then you want to just think through each step, how you want your students to engage in the process. Of course, you want to begin with the end in mind. Communicate with the students, the expectations, and then just give it a try. And that's what happened with the 5th and 6th grade teachers. They just picked something that they were doing that integrated their standards and gave it a try. Are there any questions or comments? Well, I want to thank you for the opportunity. I apologize for the rough spots at the beginning.
Thank you for attending our webinar. I invite you to check out our website, www.proedtn.org, and check out our free educator resources that we update on a monthly basis. Thank you, and please join us for future webinars.